Have you ever stared at a wall of text after your program unexpectedly stopped, feeling a bit overwhelmed by hundreds of lines of code that you did not even write? It is a common experience for developers, like trying to find a specific answer hidden within a massive digital encyclopedia. What makes a stack trace frame irrelevant to debugging is primarily its origin in well-established library code, framework internals, or language runtime components that are unlikely to contain the bug you are trying to fix. These are the parts of the trace that show how your code interacts with the underlying system, rather than revealing the flaw in your specific application logic. The core reason these frames are often irrelevant is based on the principle of abstraction and trust. Modern software is built in layers, with your application code relying heavily on battle-tested libraries and frameworks. These foundational components have typically undergone extensive testing and are used by countless other applications, making a defect within them a rare occurrence for a typical application bug. Their presence in a stack trace usually indicates that your code triggered an issue within them, not that they themselves are broken. To effectively identify and filter these frames, look for common patterns such as package names belonging to your programming language's standard library, third-party libraries you installed, or the framework you are using. For instance, in Java, you might see many frames beginning with java.lang or sun.misc. In Python, you might encounter frames from site packages. These frames are essential context but typically not the source of your application's bug. Focusing on the frames closest to your application's specific code base, often at the top of the trace or just after the known library calls, will point you towards the real problem. This practice introduces you to the concept of stack trace noise. Recognizing and filtering this noise dramatically reduces your cognitive load and helps you pinpoint the exact interaction that led to the error. An experienced debugger implicitly understands these patterns, efficiently skipping over many frames to zero in on the relevant application code. This skill is critical for debugging complex systems, particularly those with deep call stacks involving numerous third-party dependencies or asynchronous operations. By understanding and deliberately ignoring these irrelevant frames, you transform a daunting wall of text into a focused roadmap for debugging. This allows you to quickly identify where your code deviates from expected behavior, leading to faster problem resolution and a deeper understanding of your application's internal workings.
If this helps you fix faster, like, subscribe, and keep debugging with us.